Hola chicos, hoy tenemos una lección muy fácil. ¿Quién puede traducir? Si tú puedes traducir, ah, tú deberías digitar en el chat. Hablo mucho español hoy. Es muy divertido. Es muy divertido. ¿Quién puede traducir? Hoy nosotros tenemos una lección muy fácil. Sí. Ok. Espero los otros estudiantes. Esperando los otros estudiantes. Tengo mucha energía hoy. Okay, I'm going to get started. So, let's start off with a little review of what we've learned today, or learned so far in this unit. Okay, we've learned about torque, which is denoted by the Greek variable tau, and it's equal to perpendicular component of the force times distance. So torque is basically a twisting force. That's what a torque is. Okay? And we've learned how to solve rotational equilibrium problems, how to calculate net torque, and so on. Then we also have this concept of rotational inertia. Which is denoted by I, and it's equal to the sum of mr squared. The rotational inertia has the interpretation that it is how difficult it is to start or stop a rotation. And we're not talking about friction. Okay, friction exerts a torque. So friction is like a counter torque to your own torque. But rotational inertia is in the absence of friction. If you could just, how difficult is it to start or stop the rotation? Okay, so that's what we've learned about so far in rotational dynamics. Today, we're going to learn that there is an analogy between linear and rotational motion. Okay, so I'm going to express this analogy as a table. Okay, so in the top row of the table, we're going to talk about linear motion. And in the bottom row, we're going to talk about rotational motion. Okay, so for linear motion, we have a force F. So a force F is a push or a pull that moves something from point A to point B. Okay, so what is analogous to a force when we're talking about rotations? What makes something rotate? So a force makes something move in a linear sense from point A to point B. What makes something rotate a certain amount? Type it into the chat if you know. Si tú sabes, digitar en el chat. And then also, we learned about this concept of mass, which is denoted by m. Mass is what determines how difficult it is to move something, to push something from point A to point B. Okay, so we have something that is analogous to mass. All right, looks like no one wants to answer. So the thing that is analogous to force is torque. Okay, so a force is a push or a pull that moves something from point A to point B. A torque is a twist that rotates something from a certain amount. Mass determines how difficult it is to push something. Okay? Things that are very massive are difficult to push from point A to point B. All right? Things that have a lot of rotational inertia are difficult to twist. Okay? So there's this analogy. Force is analogous to torque. Mass is analogous to rotational inertia. Okay? We learned some other quantities in linear motion. We learned about the linear displacement, which is denoted by delta x. We learned about the linear velocity, which is denoted by v. And we learned about the linear acceleration, which is denoted by a. So the topic of today's lesson is what is analogous to linear displacement, what is analogous to linear velocity, and what is analogous to linear acceleration. That's what we're going to talk about today. Okay. And so basically what we're talking about is, now these three quantities were the subject of linear kinematics, and today we're going to learn about angular kinematics. That's the topic of today's lesson. Okay? And so the first quantity that I'm going to discuss is denoted by theta. And theta is called the angular position. Okay? The angular position. So, for example, if you have a beam, so the angular position describes basically the orientation of an object. Okay? If you have a beam that's horizontal, it has an angular position of 0. Okay? If you have a beam that is, I don't know, like this, okay, then we would just measure that angle, and so that has an angular position of approximately 45 degrees. Okay. So you could, as the units of angular position, you could measure angular position in degrees, but this is actually the only part of the course where we're actually going to be using radians, okay? And I'll explain why in next week's lesson, but it turns out that radians is the unit that we want to use when we're talking about angular kinematics. So just to remind you about radians, a full circle going around a full time is 2 pi radians. Going around a half time is pi radians. A quarter time is pi over 2 radians, and so on. Okay. So there's a quantity called delta theta, which, now remember, delta is means final minus initial. So delta theta is your final angle minus your initial angle. It's the change in angular position. Okay? Which is also known as the angular displacement. Okay? So that's called angular displacement. So angular displacement is analogous to linear displacement. So angular displacement. Delta theta. Okay? So if we were doing a problem where we were 100% focused on rotations, then we would just call it the displacement. Okay? If we were doing a problem where it was 100% about a car moving from point A to point B, we would talk about displacement, and that would mean delta x. Okay? So if it's clear, we can just say displacement, and that might mean delta x or it might mean delta theta. But if you're doing a problem where you have both and you need to differentiate between the two, so a good example of that would be something that is rolling. If something is rolling, then it's moving from point A to point B, so it has linear displacement, but it's also rotating while it moves, and so it has angular displacement. So when it's important to differentiate between the two types of displacement, you would say linear displacement and angular displacement. Okay? All right. So let's do a little example with this. Let's say you have something, you have a rod, okay, and the rod moves from here. This is supposed to be like a 45-degree angle. It starts out here, so I'll put 0 for initial, and it rotates right here, and it ends up at that location. Okay, so what would be the delta theta in this case? Well, it's moving 3/4 of a half circle. So we know a half circle is 1 radian, or pi radians, excuse me. Pi radians is a half revolution. So that means 3/4 of a half revolution would be 3 pi over 4, right? Because you have pi as a half circle, and it's 3/4 of a half circle, so it's 3 pi over 4. That rotation is in the clockwise sense, so that is a angular displacement of negative 3 pi over 4 radians. Okay? As another example, we could talk about something that starts out here. Oops, you guys can't see that. Starts out here, there's its initial position, and it goes like that, and it ends up over there. Okay? Type it into the chat if you know the angular displacement in that case. I will wait. Esperaré. Right, plus pi radians. Because it's a half circle in the counterclockwise sense. Excellent. So, you know, obviously the units of delta theta are also going to be radians. But there are some other units that are common out there. So, you know, you could also talk about degrees. So remember, 2 pi radians is equal to 360 degrees. And another fairly common unit is revolutions. So 1 revolution is a full rotation. So that's the same thing as 360 degrees. Okay. Oh wow, someone figured out how to put a emoji of a pie on there. That's pretty cool. All right. So the next quantity that I want to talk about is the rate of change of angular position. Okay, which would be equivalent to how fast something is spinning. Okay. And so that would be the angular displacement divided by the time elapsed. And so that is denoted by omega. This is, okay, this is the Greek letter omega. So that's a lowercase omega. You might have seen the uppercase omega is this one. It's a watch brand. And so this is called the angular velocity. Okay? It's how fast you spin. So the units of angular velocity are going to be radians per second. Okay? You could also use, you may also see degrees per second. Yowza. I have a friend who works on COVID tests, works at a company that processes COVID tests. And so right now, so I just got a text message that is the positivity rate of COVID tests right now. And so this company is running tests, and 20% of the tests right now that they're running are positive. So that's a lot. That doesn't mean that 20% of people have COVID. It means 20% of the people who chose to get a test have COVID. Someone put Kratos. Yes. If you play God of War, you know the Greek letter omega. Go ahead and type it into the chat if you know what is the unit of angular velocity that is used in the automotive industry. You can actually see this on the dashboard of your car. Okay. Type it into the chat if you know that the unit of angular velocity for the automotive industry. This would be the angular velocity of the drive shaft of your engine. So while I wait, I'm going to type it in. So the analog of linear velocity is angular velocity, and it is denoted by omega. Excellent. Yeah, RPM. RPM is a unit of angular velocity, revolutions per minute. Okay, so when you look at the RPM dial on your car, that's telling you the angular velocity of the drive shaft of your engine. Now, the RPM of your engine is not necessarily the same thing as the RPM of the wheels of your car, okay? Because your car has a thing called a transmission, which is basically a bunch of gears that are transmitting power from the engine to the wheels, and so because of the system of gearings, the rate of spin of the wheels is not going to be the rate of spin of the drive shaft, okay? But that RPM is measuring the RPM of the drive shaft itself. Let's do an example. An object does 8 clockwise rotations in 3 seconds. What is the average angular velocity? Okay. And so what we would have is delta theta over delta t is omega. So what is the angular displacement? Well, we did 8 rotations. So 1 rotation is 2 pi radians. And so that means that 8 rotations are going to be 8 times that. So that would be 16 pi radians. And it's clockwise, so that means it's an angular displacement that is negative. Okay, so that's the angular displacement, negative 16 pi in 3 seconds. So working out the math on that, you will get negative 16.8 radians per second is the angular velocity. Okay? The next topic is the rate of change of angular velocity. So that's basically how fast you spin fast. Okay, how fast you spin fast. So the definition of that would be change in angular velocity divided by change in time. And that is denoted by the Greek letter alpha. This is the Greek letter alpha. And that is what is known as the angular acceleration. Okay. So the angular acceleration is analogous to the linear acceleration. Alpha kind of looks like a fish. So the units of angular acceleration are radians per second, also known as the radians per second squared. Okay. You may also see degrees per second squared. Okay. No one uses this unit of angular acceleration, but a valid unit of angular acceleration would be the RPM. PM. I've never heard anyone use revolutions per minute, but it would be a unit of angular acceleration. I just think it's goofy to say. RPM, PM. Don't use it, though. No one else uses it. Okay. So I'm going to divide the remainder of my piece of paper in two. All right. And on the left-hand side, I'm going to write down what we had for linear motion. And this is on the left-hand side. And on the right-hand side, I'm going to write down what we have learned about for rotational motion. Okay? So we learned these kinematics equations for linear motion. We talked about these extensively. And what we learned is that if the linear acceleration is a constant, we had three equations. We had an equation that was delta x equals v naught t plus 1/2 at squared. Hopefully you remember that one. Or not necessarily remember, because you can always look it up in your notes, but you recognize that one. Hopefully you recognize that. There's the equation v final equals v initial plus at. And there was the equation v final squared equals v initial squared plus 2a delta x. So we have an analogous set of equations for rotational motion, and these equations apply if alpha is constant. So on the left, these equations are true if the linear acceleration is constant. On the right, these equations are true if the angular acceleration is constant. And so what I'm going to do is I'm just going to write down the exact same equation, but I'm going to replace each variable with its angular analog. Okay? So the analog of linear displacement is angular displacement. The analog of initial linear velocity is initial angular velocity. Time is just time. There is no time is the same whether you're talking about linear motion or angular motion. Plus 1/2. The analog of linear acceleration is angular acceleration times time squared. So that is the first kinematics equation written in the way of angular kinematics. Okay. The second equation is going to be omega final equals omega initial plus alpha times time. And the third equation is going to be omega final squared equals omega initial squared plus 2 alpha delta theta. I always feel like I'm in a fraternity or something, or when I'm teaching about rotational motion. It feels like alpha delta theta. If I founded my own fraternity, I would call it alpha delta theta. Okay. But we can go even further. So you might remember that if you have a position time graph, the slope was the velocity, and if it was bendy, if the graph was bendy like that, that is linear acceleration. The same idea holds if you had an angular position versus time graph. Okay? If you have an angular position versus time graph, the slope is angular velocity. If you have an angular position versus time graph and it is bendy, then that means you have angular acceleration. Okay? The heck? If you have a linear velocity graph, positive velocities meant going to the right, negative velocities meant going to the left. Okay? If you have an angular velocity versus time graph, positive velocities means the thing is spinning counterclockwise. Negative angular velocities means it's spinning clockwise. The slope of the linear velocity versus time graph was interpreted as linear acceleration. The slope of an angular velocity versus time graph is interpreted as angular acceleration. You might also recall that if you had a linear velocity versus time graph, the area under the curve was interpreted as the linear displacement. If you have a graph of angular velocity versus time, the area under the curve is interpreted as the angular displacement. So it is completely analogous. And for that reason, I'm not really going to do any examples because I think you can figure it out because we spent so much time on linear motion that really you don't. If you know linear motion, you know rotational motion. It's the exact same types of problems. It's just the interpretation is a little bit different because we're talking about spinning, not going from point A to point B. All right. So yeah, that's pretty much my lesson today. So I'm going to ask, ¿piensen ustedes que mi lección hoy fue fácil? Did I tell the truth? Did I tell the truth when I said that my lesson today is easy? Okay, good. I'm glad. So since it was easy, let's go ahead and go to the Zoom room. I will see you there.